Hello everyone and welcome to another lecture. Today, before we jump into Mathematica, we want to discuss the topic that is the reduction formula for integration. There might be cases where the analytic solution of a definite integral is not possible. So in those cases, either we have to approach numerically, or there might be a recursion relation or so-called reduction relation that plays an important role while numerically evaluating the integral. So as you can see already, I have written something down. The first problem, that is I denoted with 1, that is the integration of x to the power n and sine x. Oops, I didn't write the measure, that is dx. I should have written that. So you can see that this is the main thing, that is this is the function xn sine x, and I want to integrate it with respect to x. And if I do integration by parts, after a few lines of integration by parts, I get this recursion relation, that is in pi to the power n minus n into n minus 1 times I of n minus 2. This is the recursion I have after a few steps of integration by parts. And this is very painful doing by hand, that is doing this recursion and all that. And even in some cases some of the integral diverges. So by doing it in hand and without plotting, there is no easy way to tell whether this integral converges or diverges. So that's why we want to do it in Mathematica. So now we want to jump into our Mathematica interface and see what happens and how can we do it. So now we turn to Mathematica to evaluate this reduction formula that we saw for the integrand x to the power n sine x, where the lower limit was 0 and the upper limit was 1. So the first thing to do is we have to declare a function, because those integrands were functions of n, right? And we want to use this n to build up a recursive relation that we already did, and we want to put it in Mathematica and we want to evaluate. But if I write capital I and this is how I want to declare a function, there will be some problem. The reason being, I is actually protected as a symbol that is reserved for the imaginary I, the imaginary unit. So instead of I, let's choose P. As long as you understand what you are doing, it's completely fine. So okay, let me get rid of this cell. So first we declare a function. Let's call it P of n, since we are dealing with n. And now I want to type that function, that is integrate. Remember, this is a function of n, not x, so keep that in your back of the head. So first write x to the power n, and then you type sine of x, then you type x 0 to 1, right? If you run it, nothing will happen, because this is just function. This is just a function. It's not returning anything. And the recursion relation we had was something like this. Let's put a semicolon over there so that we don't run into any trouble. So the recursion relation was P of n. Since this is a function, I'm calling it a function type thing, is equals to, let's say, pi. You can always write pi like this, or you can switch to symbols, whichever way you like. So that would be pi of n minus n times n minus 1, and then you want to type p n minus 2. Now notice one thing, that when we want to do a recursion, then we need some initial data. By that I mean, if you take n equals to 2, then you will have a p of 0, and on the left hand side you will have a p of 2, right? And This is how it will be interrelated. So at least we need one data, but we will see that here we will need two datas, because when that means some two initial datas, and from those two datas we can construct the other results. Also note that here we are considering n is greater than 0. N is greater than 0, because if your n is less than 0, then it will go down and down, and this thing actually will kind of diverge. So, and we want to see what happens when n is greater than 0. So if you start from n equals to 1, you cannot do it, because that will give you a p of minus 1, and that would correspond to a p of 1 and p of minus 1, some relation like this. So the minimum n we should start from is n equals to 2. But before we proceed, we note that if n equals to 2, then this guy will become p of 0, something we haven't calculated yet, and this will become p of 2, right? And if I put n equals to 3 on the right hand side, then on the left hand side this will become p of 3, and on the right hand side we'll have p of 1. So you can see this p of 0 and p of 1, we need to know them first, just so that we can get p of 2 and p of 3. So p of 0 and p of 1, those two data will be my initial data, and the rest of them we can construct from them by using this recursion relationship. So to do that, since we already had this definition, this one, let's try to just see whether we can do it. Like, I type p of 0. Do I get something? Yes, I do. I do get something. That is great. But notice that whether it's actually working or not, because let's say I put n equals to 0, right? So this is just sine x, and integration of sine x from 0 to 1, and those that will be cos x. So yeah, this is right? Alright, so now I want to see that whether it will work for p of 1 as well. It should. Assuming and show output. So these are my outputs, right? Okay, so far so good. So let's see whether we can use these things to actually evaluate what we want to evaluate. That is, we want to see this recursive relationship, and we want to see this in a table form. The reason for that is very simple, that the results will appear in an organized manner, so that we can know what is going on. And to evaluate this recursive relationship, today we are going to learn a new command that is called do. It's a loop, and this loop will be used to solve this recursive relationship. So let's try to see what do command does first. So just type do. You will see that a suggestion appearing, and there are two arguments mainly, that is the expression, and you can see that it's saying it evaluates this expression n times. Now you can actually customize this do, that is how many times I want to do it, how many recursions I want to do actually. So what I want to do is that I first want to write this recursive thing. So p of n, and since we have seen that for p equals to 0 and p equals to 1, we already get our values from the function defined in the first line, let's just write this recursion and see what happens. So this will be, and note that I'm using equal because this thing is true. That means they are equal to each other. They're not, the right hand side is not stored in the left hand side. 1 equals means the right hand side is stored in the left hand side, and 2 equals means these are equal. That means they are true. Right hand side equals to left hand side. That's how you do it in coding language. So without further ado, let's just write these things down. Oops. So this is pi of n minus n into n minus 1, and now I want to write p of n minus 2, right? Now what you can do, you can actually say on which index to iterate and how many times you want to iterate it. So I want to iterate over n, right? And I want to start from 2, because as I mentioned earlier before, we have to keep n always greater than 0. So I have to start from 2, I mean equal or greater than 0, sorry. So I want to start from 2 and I want to go up to 10. Alright, so this is the thing I want to do. But if I do that, I run this code, can I see anything? It seems not, right? So what Mathematica is doing is that it has evaluated it, but it's not showing any output because I haven't told Mathematica, hey, show me. So I want to see this result in a table form. To do that, let's write the following command, and this is also a new command to us. So today you can also learn how to form a table in Mathematica. But before I write the table command, I want to show you the print command. If you just write print, you put third braces, and first thing I want to print is that n. That is for how many iterations, and on the right side of the table I want to see the value of my integration. That is, on the right side I want to see p of n. You could also write it I of n, but just for the sake of consistency I write it as p of n. So you do that, and finally we want to form our table so that we can see our result. So first you have to do what you have to do, you have to do this table form. You have to put third braces in it, and to know more, prints with if you just put your cursor over there, it will tell you that it prints with the elements of list arranged in an array of rectangular cells. That means it just forms a table. And then again you have to type something called a table. So the second table you just typed inside the table form, these are actually array of data, and the table form will take those array of data and put them in a very nice manner. You will see very shortly. And I want to have my n's, and I want to have my p of n's. But here I'm giving third braces as well, sorry, second braces as well, because on this side I want to show that for how many iterations. So I put again n equals, n comma 2 comma 10. So we are done, and let's run this. And as you can see that the results have appeared, but it took some time because these are pretty heavy numerical calculations, and that's why it took a bit of time. And what you can do, these things look a bit messy because you can see that there are this cos 1, sin 1s and all these stuffs. So what you can do, instead using this table over here, you just type n, that is the numerical values, and you just run it again. It will take a bit of time. Again it's running, but it's taking a bit of time, and you can see that numerical values are quite nice, right? And then you can even go on and take the suggestion, for example plot points. If you do it, it said joined true. So by joined true, it means that it takes these points, and it's the n versus the pn curve. So by joined true, Mathematica just joined these points, and let me just make this argument into false and see what happens. You can see that these points are going like this. So this is a very nice visualization of what actually went on in that integration. So the second problem we are going to consider is similar, but this time let's call it with q of, let's say m, not n, rather m. So this will be defined by, oops, something is wrong, no, and this is defined by x of n, x to the power m times exponential of x and dx. So, and we have integration from 0 to 1. So again we type integrate, and after that we have to type x to the power m, then we type exponential, we type power, we type x, and then we just specify the integration variable and the limits, right? And we now can either write the recursion relation directly or specify the initial conditions as well. So the recursion relation for this integration will turn out to be like the following, and it will look something like this. So let me write it down qualitatively first. So it will look q of, let's just choose another dummy variable k, let's say, because this k will be summed over just like n in the previous problem before, and this is just the exponential minus k times q of k minus 1. Let me put a space there so that Mathematica doesn't get confused. So as you can see, for this we can start from k equals to 1. That is my dummy variable, that one being summed over while we evaluate the recursion relationship. We can start from k equals to 1. And if I do that, on the left hand side I'll have q1, and on the left hand side I'll have q0. And can I evaluate q0 from the defined function this? Yes, I can, because if I put m equals to 0, this becomes just e to the power x dx, right? So it is also coming from here, but still let's just write it like this. Let's just define this. Q of 0 equals to integrate So instead of m, we'll just give 0. So x to the power 0 is just 1. So this is just exponential to the power x, comma x, comma 0, comma 1. Right? Let's just not evaluate it right now. Let's just keep it there. And we have written this thing already. So let's just type a do expression. And we do this do expression or do loop. We put this equality sign, and now what I want to do, I want to specify, I want to start from k equals to 1 and I want to go to up to 20, k equals to 20. So after that, what I want to do, I want to form a table, and I want to print first. So I want to print k, that is a string. You type string like inside this apostrophes, and let's put some space over here so that we can get some more space. Yeah, that should be just fine, I think. Yeah, and just type q of k. This is the thing we want to print, and then we want to form a table. So we do this table form. Again we type table, and then we specify one list where we want to have k and q of k, and we want to specify k runs from 1 to 20. So let's try to run this whole thing. So as you can see, I really had to wait for a while, and you can see these numbers and their figures, they're just really very big, and Mathematica has given you the complete result, I won't bother plotting it because these numbers are huge. For example, take this number. How many digits does this have? It's like 3, 6, 9, 12, 13 digits. And you can even plot this. Just use these plot points, and Mathematica plots it beautifully. And you can see that this integral actually converges, because this at every point, it's whenever this thing for every n, that is, as n increases, this guy goes down, 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 and down. So this is how you can make your life really easy by evaluating these recursive or reduction formulas using Mathematica. Hope you enjoyed it, and I'll see you on the next lecture. Thank you.